There are objects in the universe so extreme that even our best laws of physics begin to feel negotiable. Places where space is no longer a calm stage, but something flexible, stretched, bent, where time itself slows down, and light, the fastest thing we know, can be trapped forever. This is not a star. This is not a galaxy. This is gravity taken to its absolute limit. And somewhere out there, far beyond what we can ever reach, exist not one, but multiple versions of this nightmare. Today, we're going to meet two of them. One is famous. Its name echoes across documentaries and comment sections, TON 618. The other is quieter, but whenever TON 618 is mentioned, someone always replies with the same words: Phoenix A is bigger. So the question is simple. Which one is the true final boss of the universe? But before we compare them, we need to understand something deeply unintuitive. How can the darkest objects in existence become the brightest lights the universe has ever produced? TON 618 lies near the border of the constellations Canes Venatici and Coma Berenices, more than 18 billion light-years away. So far, that the light reaching our telescopes today began its journey when the universe was still young, less than a quarter of its current age. When astronomers first noticed it in the 1950s, it didn't look special at all. Just a faint, bluish point of light. A star. Or so they thought. But when its light was broken apart, when its spectrum was analyzed, the illusion collapsed. This was no star. It was the blazing core of a distant galaxy, powered by something far more extreme, a quasar. Here's where intuition fails us. A quasar is not a thing, it's a phase. At the center of almost every galaxy, there is a supermassive black hole. Most of the time, these giants are quiet, dormant, invisible. But when vast amounts of gas and dust fall inward, something extraordinary happens. Matter spirals toward the black hole at incredible speeds. Faster, hotter, denser. Friction inside this swirling disk heats the material to tens of thousands of degrees. And before that matter disappears forever, it releases an enormous amount of energy. Across the entire electromagnetic spectrum, radio waves, visible light, X-rays, even gamma rays. The result is a cosmic beacon so powerful it can outshine an entire galaxy. That is a quasar. The black hole itself remains dark, but the chaos around it lights up the universe. This is the great paradox of black holes. The darkest objects ever discovered create the brightest light we have ever seen. TON 618 is one of the most luminous quasars known. Its energy output rivals the combined light of hundreds of trillions of stars. If TON 618 were placed at the center of our own Milky Way, it would erase the night sky completely. Stars would vanish into the glare. The galaxy would glow like an eternal artificial dawn. At the heart of that radiance lurks the true monster, a black hole with a mass around 66 billion times that of our Sun. Its event horizon, the boundary beyond which nothing can escape, is so vast that our entire solar system could disappear inside it, and still have room to spare. This alone would make TON 618 one of the most extreme objects ever discovered. But this is where the story takes a turn, because TON 618 may not be the biggest player in the game. Enter Phoenix A. At the center of the Phoenix cluster lies another supermassive black hole, even heavier, possibly more massive than TON 618 itself, depending on how you measure it. This is where online arguments are born. Which one is bigger? Is it mass, the size of the event horizon, the power output, the influence over its host galaxy? Because in cosmic terms, big is not a single number. Phoenix A may outweigh TON 618, but TON 618, during its quasar phase, may have released more energy into the universe. One dominates by mass, the other by fury, and both push our understanding of physics to uncomfortable places. But numbers alone don't capture the true scale of these objects. So let's ask a more disturbing question. What if one of them sat at the center of our own galaxy? Imagine looking up at the night sky and realizing there is no night. The core of the Milky Way would blaze brighter than the moon, brighter than thousands of suns combined. Radiation would flood interstellar space. Star formation would be disrupted. Entire regions of the galaxy could be reshaped. Civilizations, if they emerged at all, would grow up beneath a sky dominated by a single blinding presence, a cosmic god of light and gravity. And yet, this is still only the surface of the horror, because the truly strange effects of these objects do not involve light. They involve time, and beyond a certain invisible boundary, time itself begins to lose meaning. What happens if you fall closer? What happens at the edge, where escape becomes impossible? That is where the universe stops giving us clear answers. And that is where the next part of this story begins. If you were falling toward one of these giants, something strange would begin to happen long before you reached it. From your perspective, nothing feels unusual at first. No sudden jolt, no invisible wall, but to a distant observer, watching from far away, your descent would appear to slow. And slow, and slow even more. Near the event horizon, seconds for you would stretch into years for the rest of the universe. Light emitted from your ship would struggle to climb out, losing energy as it escapes gravity's grip. Colors would shift. Blues would fade into red, red into darkness. This is not science fiction. It is a direct consequence of Einstein's equations, and yet, the moment you cross that invisible boundary, our mathematics falls silent. Inside the event horizon, space and time exchange roles. There is no known path back. No signal can return. At the center lies the singularity, a point where density becomes infinite and our models of reality simply stop working. This is not because we lack intelligence. It's because the universe is forcing us to confront the limits of knowledge itself. But perhaps the most unsettling mystery is not what happens inside these objects. It's how they came to exist at all. TON 618 was already enormous when the universe was still young. So young that, by conventional standards, it should not have had enough time to grow. Black holes grow by feeding. They consume gas, dust, stars, and occasionally, each other. But there is a speed limit. Feed too fast, and radiation pushes material away. This creates a natural cap on how quickly a black hole can gain mass. And yet, TON 618 somehow reached tens of billions of solar masses in just a few billion years. That should not be possible. At least, not according to our simplest models. So astronomers began to search for alternatives. Perhaps the first black holes were born unusually large. In the early universe, conditions were extreme. Vast clouds of pristine hydrogen and helium drifted through space, untouched by previous generations of stars. Under the right circumstances, these clouds could have collapsed directly into massive black holes, skipping the star phase entirely. Another possibility involves something even stranger: quasi-stars, hypothetical objects where a black hole forms inside a giant star-like envelope, feeding rapidly from within. In this scenario, the black hole grows quietly and efficiently, hidden behind a brilliant shell. These ideas remain speculative, but they exist for a reason. Because objects like TON 618 demand them. They force us to invent new explanations to avoid admitting defeat. And the early universe itself may have helped. Back then, galaxies were smaller, closer, and far more chaotic. Gas was abundant. Collisions were common. Black holes didn't have to wait politely for fuel. They were immersed in it, fed continuously, violently. It was a cosmic buffet, and the largest guests grew faster than anyone expected. Phoenix 8 likely followed a similar path. At the heart of a massive galaxy cluster, surrounded by immense reservoirs of gas, it may have continued feeding for billions of years, growing heavier, quieter, but no less powerful. So why should we care about these monsters if they are so distant and so unreachable? Because quasars are more than cosmic curiosities. They are lighthouses. As their light travels toward us, it passes through the gas-filling intergalactic space. Each cloud it crosses leaves a subtle fingerprint in the quasar's spectrum. By studying those fingerprints, astronomers can map the distribution of matter across the early universe. They can measure chemical composition, track the growth of galaxies, and reconstruct cosmic history. In a strange way, these destructive engines have become our greatest guides. They illuminate the invisible. So which one is truly greater? TON 618, with its furious brilliance and staggering output, or Phoenix A, with its crushing mass and silent dominance? The answer depends on what you value. If power is measured in light, TON 618 burns brighter. If power is measured in weight, Phoenix A may win. But both share something more profound. They remind us that the universe is not obligated to make sense. And perhaps the most unsettling realization of all is that what we see today is not what exists right now. The light from these objects left billions of years ago. We are not observing the present. We are observing memory. Snapshots frozen in time, delivered across a vast and expanding cosmos. TON 618 may be larger today, or quieter, or something else entirely. The same is true for Phoenix Aphers. There are realities out there we will never see as they are, only as they were. And that raises one final, uncomfortable thought. If the universe is a record of its own past, what does that make us? Observers of echoes, trying to understand a story that is always one step ahead of us. There is a quiet truth hidden in everything we observe in the universe. We never see things as they are. We see them as they were. Light is not instant. It travels. Every photon that reaches our eyes is a messenger from the past. When we look at TON 618, we are not witnessing a living, active monster in real time. We are seeing a snapshot, a moment frozen billions of years ago, when the universe itself was young and turbulent. Phoenix A is the same. Whatever it is doing right now, feeding, resting, growing, fading, we will not know for billions of years. The universe does not show us its present, only its memory. This realization can feel unsettling. After all, if even the largest, most powerful objects in existence are visible only as echoes of their former selves, what does that say about our place in the cosmos? It says this: we are latecomers. We exist in a universe already ancient beyond comprehension, trying to understand events that unfolded long before our planet even formed. And yet, somehow, we can still reconstruct that story. From a small, fragile world, orbiting an unremarkable star, in a quiet corner of a vast galaxy, we have learned to measure invisible forces, to decode light, to test ideas against the universe itself. That alone is extraordinary. Black holes like TON 618 and Phoenix A are often described as monsters, and in many ways, they are. They consume, they distort, they dominate, but they also teach. They show us how galaxies grow, how matter moves, how space and time respond to extreme conditions. They force us to confront the edges of knowledge and admit when our answers are incomplete. In doing so, they make science honest. There is something deeply human about standing at the edge of understanding and refusing to turn away. We may never know what truly lies beyond an event horizon. We may never see these giants as they exist today. But we can ask the questions. We can build better instruments, refine better theories, and slowly, patiently, push the boundary a little further back. Not because the universe owes us answers, but because curiosity is what we do. So which one is the true final boss of the universe? Tuan 618, burning with unimaginable fury, or Phoenix A, quietly outweighing nearly everything else we know? The honest answer is that the universe does not care which one we choose, but the fact that we can even ask the question means something profound. It means that, in a universe filled with darkness, we have learned how to see. And in a cosmos defined by silence, we have learned how to listen. So now, the question is yours. Which one do you think deserves the title, and why?